So last lecture I described the quantum search algorithm constructed by Love-Grover. I will repeat it again because there are lots of physical concepts which are connected with it, and it also connects to many applications for the same reason. Okay. So the algorithm was very simple. You want to have a database which I will just call it I. Last time I think I called it Xi, just saving some writing. And there is a target which is some state t. And you want to go from a completely unbiased distribution of the initial database to the final target. And that was achieved by the simple algorithm, which was U acting on the state S is equal to T, and you have to iterate this algorithm number of times, which I called Q. The operator U was a unitary operator made up of two reflections, and the state S was a uniform superposition. So if the size of this database is n, then this is an unbiased distribution. And the algorithm does the job by this particular evolution, and the property which I illustrated. So the evolution is along the geodesic in the two-dimensional plane defined by these two states, uniform superposition and the target. And this is in some sense directed evolution in contrast to random search, because you are not given any property of the state except for that one oracle, and classically there is nothing you can do with such a situation except look up various possibilities randomly, like finding somebody's name in a telephone book given the telephone number. And that is what you will do classically, but this algorithm is a directed evolution. The unitary operator is deterministic, and it can be reversed if you want. No problem with that either. So this is written in a quantum language, but you can also write it using linear algebra. Sometimes it helps understanding. So what are these operators? So I defined RT as identity minus 2 times the projection, and if you want to now construct a matrix for this, it is quite straightforward. It is everywhere 1, except that there is a minus 1 in the location of t. Okay, this is n by n matrix because we are working in n-dimensional space. So this is a location of T. The other operator, which is actually it's better to write this minus Rs, and that is 2 times the projector minus identity, the minus sign because I flipped from this to that. And what does it do? Well, just let us write down given this particular structure. So there is a minus identity, so minus 1 will be there on the diagonal everywhere. And what does this do? Okay, this is a column vector S. All the amplitudes are equal. Okay. And you have to square it, so it will give a matrix which has 1 everywhere. Because that is what the, well, not 1, but 1 over n everywhere because of the normalization. And there is a 2 here, so more explicitly it is, you have to add 2 by n at all locations. And the diagonal has that minus 1 extra, and the other one are all 2 by n everywhere.
Can be considered as the density matrix of the representation?
Yeah, it's just writing this explicitly as a matrix in this basis labeled by I. Okay. I is well, some label of the database, whatever you want to construct, and in that basis, this is what it looks like. Now, this matrix has some extra unusual properties. One of them is because it's a reflection operator, if you square it, you will get identity. Okay. You have to multiply this by this and you will find that there will be 4 over n square appearing for every column over here. There is minus 4 over n when you square this, that cancels out. And then this minus 1 gets squared to 1 and it becomes identity. It's directly obvious because it's a reflection operator. You interpret it in one way. But there is another feature, and that is if you add up all the elements either along any row or any column, that is also identity. No squaring, just sum up. 2 by n, n number of times will give you plus 2, there is a minus 1, that adds up to 1. So, what does that represent? So, the conservation because of that 1, that if you distribute over a whole space, normalization is maintained, and this is the characteristic of a process in physics which is called diffusion. You go from one state to various other neighboring possibilities and the sum of that thing is conserved. So it is simultaneously both reflection and diffusion properties are satisfied. And it's actually quite rare. In the other words, that if you demand that you have to satisfy both reflection and diffusion operators or both properties simultaneously, find a matrix, you will end up with this matrix. There is no other solution. And that has various connections to many situations in physics, and one way, well, I will describe later, but these properties are mapped to different kind of conservation laws depending on what you want to deal with. In this label, the diffusion just refers to the location or the amplitude of the, not amplitude, whatever the label of the probability is to spread over a certain number, and the conservation refers to particle number. In other contexts, it can mean something else, and we will see what all kind of things it can connect to. But this is a unusual feature, and for that reason, this sometimes it's also referred to as Grover diffusion operator. What is the difference from classical diffusion? Is the classical diffusion will also have all numbers adding up to 1. But there will be probabilities and everything will be positive. Here the diagonal element is negative. So you are taking something from diagonal and distributing all over the place, and you allow that original location to go negative. That is a different feature compared to a conventional probability distribution, and that is why this operation has unusual consequences. It produces basically interference because there are some negative entries which are involved over there. And the classical diffusion operator in the computer science language also is many times labeled as a Markovian evolution. You start somewhere and you go to neighboring places. Here, what has been done is, it is from any place you start, you can go any other location. So this is a process which is all-to-all connectivity. Generally, in the statistical models, you start somewhere, you move with some finite speed and you go to the neighbors, not much more than that. But here you are going from one location to any other location in one step. That is a consequence of picking up this high connectivity. But it's a feature of the algorithm. There are analogs in classical physics of such all-to-all connectivity, which are labeled as a mean field theory. You average over the whole environment and take its effect into one particular location. But that is a different story. I don't have to go in that. But when I say now this reflection is in what reference frame? Okay, this way is very clear. You go to that location and flip its sign. So here now you look at this structure again. What will this operator do? If there is a component of the state along the direction S, then there is a 2 here and -1 here, it will remain unchanged. But if there is a component in a direction perpendicular to S, it will flip its sign because this will not contribute on the minus identity. So you can pick a direction, keep the component along the direction same, and whatever is transverse, change the sign of all those things. And this S is a kind of uniform superposition, so it can be interpreted as a average of all the values, whatever I are there. It's just simple statistical sum. The normalization is little bit different, but that doesn't matter. It will be taken care of this outer product over here. But because S is defining the average direction, and what this is doing is changing the sign of all the components which are transverse to it. This sometimes is also called reflection. In the average. Okay. So now I can redraw that one diagram I gave for a simplest possibility, which was this particular case, and there were 4 amplitudes, and the initial value was half. They were all equal. Then you apply this RT, which is a binary oracle. This is unbiased state, and it's nice to choose it as a equilibrium state. So if you don't do anything, it will just remain there. That is something which is a uniform distribution. Nothing happens to it if you are not going to disturb it. But then you do this application of the oracle, and I chose the oracle to act on the first state, and it is going to change its sign. So this is minus half, this one is a plus half, and this is a kind of disturbance on the equilibrium state, but it has to be sudden perturbation, instantaneous, that you take it from here to here, while nothing else happens in the dynamics. After that, I apply this reflection in the average operation. And what does it look like? Well, so this is sometime in dynamics, it is called an over-relaxation step. So here the average was 1/4, and it will remain 1/1/4, because it's with relative to this average, you are going to change sign. So whatever is on one side, you will go equal distance on the other side, and so this 3 labels reduce to 0, and this one becomes equal to 1. And it can be described as oscillation, and the reason for that is the inherent properties which has been buried inside this. So what are you actually working with? So this is a quantum language, and you are allowing positive and negative values of the amplitude, and they are interfering with each other. And that actually, from the physics point of view, is a property of waves. Waves are the features where you can have amplitudes, you can go plus and minus, and you can have interference between them. So this algorithm actually combines the properties of particles and waves together. And that is what produces the advantage of the dynamics. But if you want to understand this, the particle label is on the horizontal axis, the 4 amplitude which I have. The value of the amplitude is behaving like a wave, and that is where I put in this label like an oscillation. So now, for the time being, put aside the particle label and try to look at what happens when you have a wave dynamics. So you start with a nice equilibrium and you do a perturbation, like throwing a stone in the puddle of water. It will create a disturbance. And the properties of the waves fundamentally is it will have an equilibrium position and it will oscillate around the equilibrium position. So you define the equilibrium position as the average, you perturbed it, and it is going to oscillate it around it. If it is on one side, it will go on to the other side. So what happened between here, there is a perturbation, this are on one side, they will go on to the opposite side and keep on going back and forth. So this result is actually the opposite side of the oscillation. Imagine oscillator or just a pendulum. The equilibrium position is here, you moved it away, it will go over here, it will overshoot and go over the other side and come back and forth. So this is actually the result after half the oscillation period. You are on one side, you got equal distance on the other side. And if you don't stop, keep on going back and forth. That is a unitary evolution. You have to have a certain number of iterations. If you do too many, it is just going to go back and forth. You don't know when it will stop. You have to stop at the right moment. So opposite end of oscillation is half the period. And it's the dynamics of waves which is producing this particular feature.
So when we take the average about 0.25,
Yeah.
shouldn't that target start from 0.5, it should go to 1?
Yeah, so you have to take with respect to this is minus half, this is a quarter, the distance is 3/4. You add 3/4 to the quarter and it becomes 1.
But it is starting after 0.25 also. So again, on the other side, it will start after 0.25, it will start from the level 0.5.
No, you have to always do a reflection about whatever the average is. This is wave dynamics. Okay, the perturbation is over. Perturbation you did something which was instantaneous and it is outside the wave dynamics. But after the perturbation is over, you just let the system evolve according to its own internal dynamics. And that is just the oscillatory feature of the waves.
That means the difference is shifted to the average.
Yeah, so when you do the perturbation, the average shifts. Okay, here it was half, you give it a kick and the average become a quarter. And then you oscillate about the quarter, whatever the average is, unless the next disturbance comes along. Yeah. So, how did Grover come up with this algorithm? Well, I can mention several properties connected to it, which has to do with applications, but I will do that a little bit later. So Grover, by his own admission, was not working on this problem as a kind of a research topic. His job was in VLSI design, making sophisticated integrated circuits. So this was a kind of spare time hobby, whatever it was, he was trying out something, and he landed up with this particular algorithm. So he didn't think in this particular language to begin with. His idea started from physics. So this is a and it explains the feature which he landed up with. There was the original part of the physics, and all the quantum mechanics does is, if you are given a Hamiltonian, you solve the Schrodinger equation. Nothing more complicated than that. So the question was, what is the Hamiltonian you should choose to solve the search problem? So he wrote down the simplest thing which everybody works with as a classical or quantum, that the Hamiltonian has two parts: kinetic energy plus potential energy. Nothing more complicated than that. The difference between classical physics and quantum physics comes in that these two operators commute in classical dynamics, but they don't commute in quantum dynamics. Remember Schrodinger equation, this will be Laplacian and this will be some scalar potential. So now he had to convert this to a search problem. So he decided the potential energy, I will make a well which is kind of deep. So whatever is wandering around, if it comes over here, it falls into well. So what is the shape of the well? Well is concentrated only at the target state, and everything else, nothing happens to it. So that can be mapped directly onto the oracle. This potential energy goes to the oracle. That it has to be negative at the location of the target, and everywhere else it is constant. So now if you are moving around, if you come here, you will fall inside. That was the purpose of the search process. What does kinetic energy do? Kinetic energy basically just performs diffusion. You wander around in whatever the space is. If there is no potential energy, you will just go everywhere in some random manner. And there is a now argument of how we landed up with this particular operator. So now let us see what Schrodinger equation does. So evolution is this operator u which is different than this one. So let me give some other label. Just let me give some argument. And that is conveniently the time evolution, and the Schrodinger equation basically says that this is given by this exponential of the Hamiltonian. But now we have two terms. So it can be approximated as exponential of 1 and the exponential of the other up to higher order correction. So this is what is known as a Trotter decomposition for the evolution time, which is small. Because if you now calculate both the sides of the equation, one is same term which is linear in say delta t will also be same on both sides, and the difference will come when the term is second order. Delta t square, they will be different. So typically in lots of physics application, this approximation is used for delta t infinitesimal. Then
It's an approximation. We are directly replacing Hamiltonian by Hamiltonian.
But this is an approximation because these two things do not commute. If they commute, it will be exact. But if they don't commute, you will get a higher order term. What will be the coefficient of delta t square? It will be some commutator of kinetic energy and potential energy, which will be different on the two sides if you do a Taylor series expansion.
We take it to Taylor series, decompose it, and then again recombine exponentials.
So if they were to commute perfectly, then this thing is exact. But in quantum mechanics, we know that these operators don't commute, and that is why it's an approximation. And approximation is good if this delta t is small, because the corrections are coming at the second order. But if corrections are not small, of course it will be not equal to the other side. So this is something which is standard in the thinking of the evolution. But from this, Grover made a drastic jump. And that is use this decomposition for the largest possible delta t. So it is an approximation. So this identity is not going to work. But Grover decided I will just use this for the largest value of delta t, which is possible. So now you can ask, what is the largest values allowed for either of these two choices? Well, here the largest value is this just an exponential of a phase, and the potential energy is diagonal. So the maximum you can do is go around the circle on the opposite side, which makes -1. So then e raised to -I, this potential energy times delta t goes to exactly this oracle, which is identity minus 2. Because on a exponentiation of a phase, you can go only from 1 to minus 1. Afterward, you will actually come back to where you are starting. In this one, how far you can go. And there, again, you have to now ask what is the maximum value possible. So, for that, we will have to find a description of the standard kinetic energy, which is the Laplacian in Schrödinger equation. What you will get for a Laplacian? And well, you have to find a description of the Laplacian in this language. What does Laplacian do? So for that, it is first easy to look at just a second derivative in one direction. So if I want to calculate a second derivative of function, I will calculate function plus some value on one side, some value on the other side, and subtract something on the middle. So this is a discretization of the second order derivative. There is a 1 over epsilon square if you want to take the limit to 0. So I can make it more exact, because in the that's what you will end up in infinitesimal Laplacian. But Grover decided to use this Laplacian with the largest possible value, and he doesn't want to care about taking the limit epsilon going to 0. Now you look at this description. What is the epsilon square is just a scaling factor. What is the property of this thing in the numerator? It is a diffusion operator. You took something from a particular location and put it on its neighbor and reduce the local value. And the diffusion basically that it's a conservation, so the sum of all the coefficient equal to 0. You went somewhere here and here, the same amount has to be subtracted. So this is something which is elementary in calculus. So what is now the Laplacian? Laplacian is not just in one direction, it's in all directions. Okay. So it can be approximated in the sense that I will drop the proportionality constants as and I have to give a location because it acts on some function. So let me use a state label which I had. So this is del square of I is a summation over mu, which are the neighbors of I plus mu. So this goes over how many numbers of neighbors are there. So Let me call this D, some value I need. So suppose there are D neighbors. I take the values of all the neighbors, I increase it, and I subtract off the corresponding value from the location, just like over here. That is the diffusion description. I put 1 over D because there are D neighbors, so the sum of all the coefficients is equal to 1. So this is the structure which emerges to exponentiate it. Well, we'll just replace it by this particular process in the whole operator, and it is kind of simple enough that the sum over all the neighbors, when you exponentiate it, it retains the same property because it's completely unbiased, only the normalization changes. And what Grover did was gave in all-to-all connectivity, which means every location I is neighbor of every other location. Okay. And so you spread out from one point to all its neighbors and then subtract the local point by some particular amount. That will what will produce the Laplacian. And how far you can go? Well, there is a limit because you have to maintain unitarity. So in a unitary matrix, no element can go outside value 1. Because the sum over all the column or row, the square of the numbers is equal to 1. So it has to remain bounded inside 1. And then you ask what is the maximum diffusion you can achieve. Well, you spread out as much as you can. No element should be going outside +1 and -1 boundary. And so this 2 by n happens to be the maximum amount which produces -1. If you try to increase this even a little bit more than 2 over n, this number will become below -1 and then you can't hold it. Okay. So that is the largest diffusion operator which he could construct, and he just plugged it in. So this is what it produced. He made all the neighbors, so largest this operator which is minus Rs. And well, he jumped from this infinitesimal value to maximum value of delta t. He used the same formula and arrived at this particular structure, and that was exactly the algorithm which now you could be describing in this language of linear algebra. But this is how he thought about it. He put various things together, and it works, and it works fantastically, and it does the job, whatever was required by the Hamiltonian, that you move around on the space and there is a negative potential at some particular location and you will fall in that particular hole. But the surprise was that this algorithm also turned out to be optimal. There is nothing better you can do than this by any other tricks of any dynamics. And that has all kind of other connections, but one thing I can mention that yes, he made this large jump. So what he used was some Hamiltonian which actually is different because he used this formula for finite delta t, not for infinitesimal delta t. So I can ask, what is the Hamiltonian which he used by making this drastic jump? Okay. And that is something which can be worked out. So the effective Hamiltonian can be just defined as e raised to minus I at effective times delta t is equal to the operator which we have chosen minus rs rt. Let's just define it. Because these are unitary operators and this is also some unitary object. If delta t was really small, then you will end up with this expression, but delta t is not small. So you can now invert this expression and ask the question, what is this value? And all you have to do is take a log. So it is I by delta t log ln is actually the correct expression, but that is the result. What is the value of this? And it is not just kinetic energy and potential energy. It's not too difficult to work out because everything here is essentially happening in the two-dimensional space, S and T. So it's a 2 by 2 matrix. And any 2 by 2 matrix you can write as a polymatrix. You can take a log, no problem with all those kind of things. And this can be evaluated. And I will write down the result. I don't want to miss any normalization, so it is 2 theta by cos theta. Okay. In the convention which I used last time for defining the overlap, it turns out to be this, where I had defined the convention that sine theta was 1 over root n. Okay. So you take a 2 by 2 matrix, which I basically defined by how much you rotate at every step. And 2 theta was the rotation angle for every step. So you actually land up with this operator, which is very different. It is not a linear combination of the kinetic energy and the potential energy, which had the form of projector for T and projector for S. So it is not either this TT and SS combination, but it turns out to be this. You can stare at it for some time and rewrite in terms of the projector, and then you will land up with an interesting structure. That it is actually the commutator of the kinetic energy part and the potential energy part. It is not the sum of the two, but it is actually the commutator. So somehow by doing all this jugglery, Grover created this commutator. And this commutator gives the best evolution in terms of largest possible steps you can take to reach the final state. Okay. There is nothing complicated here. You take a commutator of these two objects, you will get a contraction between T and S, and that contraction between T and S is this object. It's just an overlap of the two states as defined. S had a normalization of 1 by root n, that's where it came from. So this is a simple identity. The normalization you have to figure out by taking a log. But that is all kind straightforward. And well, that is what he produced. So somehow Grover's algorithm does a non-trivial job by taking two operators and combining them into a commutator and producing an evolution according to that. So that is part of the algebra, but it's just playing around with various things, and as I told earlier, Grover was playing around with these things in his spare time, and he worked out this algebra, and everything basically fell into place in the right manner. Now one can ask, where can this algorithm be useful? What are the contexts in which these ideas can be applied? And there it is instructive to go back to this particular picture and see how we have put various things together. It's essentially two processes. One of them is a reflection of the target object, and another is a oscillation around the average value, which can be implemented by wave dynamics. So now you can ask, can I just look at as a problem in classical physics, or similar to what we have discussed before, reversible computation, like the billiard ball model? We are not jumping into quantum logic. And answer is yes. What you need is a reflection, and in billiard ball model all we are using was reflections. Nothing more complicated than that. What is the interpretation of this structure in that language? So there is a conservation law in the reversible logic which we use, that the total energy of the system doesn't change. Okay, and the collisions are completely elastic. Whatever is the initial energy remains the same as the final energy. And the other thing is, what do reflections do? Well, reflections basically conserve energy but change momentum. And how does the momentum change? Well, if you go to the center of mass frame, then in the center of mass frame, when you collide, it will come with some momentum, and the momentum will change its sign. Nothing else can happen because energy is conserved, so the p square, when you calculate it, it cannot be any different. All you can do is change sign. So this energy is conserved. And momentum changes sign on reflection in the center of mass frame. How is the center of mass frame defined? Well, if you have particles of all equal masses, it is nothing but the average. Okay. So, we have exactly the ingredients which we need. There were two reflections. One was a static reflection on the target, and another was a reflection in the center of mass frame. And once you realize that the center of mass frame and the average are the same, mathematical structure will just come through. There is no problem at all. So this can be implemented. So all you need is a certain kind of mapping. You have to arrange various things, and it goes. So now I can show you some videos. Yeah. Yeah. Yeah, so what you need is a system with certain features. How are you going to connect various things together? And then what you need is a oscillators, which are playing the role of wave dynamics, but they have to be coupled with each other in a certain manner. And I can show you the videos now. So this is the model. There are 4 oscillators. They are coupled by that bar on the top. This bar. And they are all coupled identically. Okay. The bar because it's coupled identically, plays the role of average or the center of mass degree of freedom. And these oscillators are going up and down at certain point. And what you need to do to implement the algorithm is reflect one of them, which means you just, when it is moving, you put an obstruction in the middle, it will bounce off. And what should happen is whichever one bounces off, it will increase in amplitude. So that you should be able to see that in this one, it's the second one which is bounced off, and it will increase in the amplitude compared to the other three. And of course, you want to implement the algorithm, you have to stop at the right moment. Okay, that once there will be some situation where the other three are almost stationary and this is moving very fast. And if you stop at that particular point, you have this state where all the amplitude is in one component. So let me play it again. Okay, initially all are equally, then one of them is bounced off. And you can see that the one which is bounced off moves much faster than the other one. Its amplitude has gone up. And of course there will be some position over here where the other three are stationary and this one is moving very fast. It's dynamics which you have to imagine in the momentum space or velocity space, because that is the quantity which is conserved. Sum of all the momentum square is equal to some constant. So there will be an instance where three momenta are small and the four momentum is very large. So that requires a little bit of imagination. You have to look at the values of the momentum and not the values of the position. The positions are continuously going up and down, and I will play it again. So that's the model. What was it? It was actually my son's high school science project. Nothing fancy was required. We just had to go to the Bangalore's market and buy these things, some springs, some weights, and we have to adjust because the couplings have to be tuned. The springs had to be cut in a proper length and the mass has to have a certain value. So those can be all worked out analytically, no problem, and then we made them. This particular structure. Things are not perfect because when you do it writing equations, you have to take into account that not only these masses have some non-zero value, the spring also has a non-zero mass. So the Newton's equation, you generally don't write any value for the spring mass, but here you have to correct for that, and those kind of adjustments will be there, but it works. So this is a simple enough thing as a high school science project, but it went very far in the sense that there is a competition held every year by Intel about its Intel Science Fair. So this won the top prize at the national level in India in the physics category, just demonstrating how this thing works, and well, together with some analytical calculations which go with it. And it also went to the international level, which is held in the US, and got lots of comments regarding that. But there is nothing fancy, and for many years it was part of the annual science day, which is held in IISc 28th of February, something like that. There's a National Science Day. All kind of people come from outside, mostly school children, and this was demonstrated to them. The model is still there. I will show it to you later, but this is essentially what it was. Some weights hanging from, as I said, it has been demonstrated many times and I got tired of it, so now it is sitting in my cupboard. But if somebody wants to play with it, it is there. So this is one interesting video, and I will show you another thing provided the network connects, which is equally mysterious. So now look at this system. It has two blocks, and there are two types of collisions which are going to occur. One is with the wall, and the other is between the two blocks. So the collision with the wall will just reverse the momentum of this particular object. That is going to play the role of oracle. Thus when this particular knowledge flips its sign. The collision between the two blocks is going to play the center of mass motion. It will just reverse the velocity in the center of mass frame. Of course, what you see is in the physical frame, but which is related to the center of mass frame in certain way. And now see what happens. It bounced off a few number of times. Number of collisions equal to 3. Some collisions with between the two blocks, 1, 2, and then 3. And other collision was with the wall. Now you change it a little bit, where you change the mass from 1 and 1 to 1 and 100. And watch this number of collisions. That is the number of iterations in some way. There are both collisions counted, so it's actually related to 2 times the query, because one was an action on S, the other is an action on T, and the system is such that the two have to alternate. There is no other possibility in the dynamics. So it undergoes 31 collisions. Proceed further. You increase the mass. Lots of collisions. Keep on looking at that number. This one goes out, but that is going to collide with the wall one more number of times. So the number is 314. Yeah, there's it is the last collision. Go one step more. Every time the weight is changing by a factor of 100. What you seeing in this number of collisions is the value of pi. Question is, how do these colliding blocks know what pi is? And that also in decimal system. And the reason is that it's implementing Grover's algorithm. See, we viewed it as rotating from some initial state to another state, the angle was pi over 2. But this RS and RT, now they are getting counted twice. So instead of pi by 2, if you count both RS and RT separately, it becomes pi. And it's exactly doing that particular job. Of course, you have to identify what is the correct initial state and a final state, because here they are well defined. It's not going to keep on going around in cycles. Some initial state you come in, final state it stops. So the pi is appearing, and why it is appearing in decimal system has to do with the values of these weights. So every time I increase the number by a factor of 100, you get one more decimal. And that is why, because the algorithm is scaling as square root of n. So if I increase the weight by a factor of 100, I get one more digit. And so, yeah, this is a fantastic illustration that you can do all kinds of things with this particular algorithm. Sometimes you get great results, and not any fancy techniques are needed. Okay? All you have to implement are simple reflections, and if you manage to do that, you can get highly non-trivial results. So yeah, this is another video worth looking at, but they are the illustrations of how far this algorithm can go. I mean, it was invented in the classical setting, in the quantum setting by putting in certain features, but now we can convert it into a reversible classical logic also without too much trouble, provided you have a reflection operation. And that is enough. There is a caveat here, so that I should point out. And for that, yeah, let me now switch off this thing, its job is over. Questions about what do you do when you can factorize the algorithm, okay? So the classical case produce this binary search, which I had described last time, that what do you do when you look up something in dictionary? You break it down, the whole oracle is now broken down into individual letters, and you look up levels one by one. You can ask, can I do something similar? Yes. And what does it amount to doing that? The oracle is a product of smaller oracles. Like in a dictionary, if you want to look for the word, you don't look for the whole word, you look for the first letter. And then you look for the second letter, and look for the third letter, etc. So this binary search factorized it, and you can say that I have now a factorized oracle available. Okay. So this complexity here is log 2n, how many steps you needed. Because you factorize it, every step you divide the database in half, and you continue, and how many steps you need to go down one object is log 2n. So the quantum version is you want to factorize, but how many factors should you look for? And that comes down to a question is with one query, how many objects you can identify? That answer is here, it is 4. That with one query I can identify 4 objects. So this is a search, but it will be executed with log to the base 4. Every step you will pick one out of 4 possibilities, but using only a binary oracle. So, and what is the advantage? Is a factor of 2. This number is half that. Is instead of going in steps of 2, now you will go in steps of 4. And this structure was interesting to me, as I mentioned last time, that this is exactly the arrangement of the genetic information in the DNA basis. Every step you are moving in a factor of 4. How it is connected, it is still an open question. It has to be ultimately settled experimentally, which requires techniques which doesn't exist right now, but hopefully it can be tested in future. But this is the structure which is important, that you can do this and you see certain patterns. There is another feature which I can also point out, because I showed all these videos, that I can now compare. Okay, so just for the smallest case, what are all the resources which are required to execute this particular algorithm? Okay. So we saw the quantum, the little table. There is a queries or oracle. And size of the space. How many times you are going to use the oracle, and what is the dimension of your systems that you can handle. So for quantum in n equal to 4, we saw the answer. This is one query it can decide. And what is the space which is required? Well, there are 4 numbers, and I can encode with 2 qubits. Okay. Then classical, which is a particle version which we naively command or connect with the Boolean algebra, all discrete states. You have 4 objects. Space is quite clear that you need 2 bits to encode 4 states, but you want to find how many queries you need. The oracle is still a binary search, and you will need 2 queries to distinguish 4 possibilities in the classical distinct label states. Okay. But I can now add a part which was illustrated by this wave dynamics videos, including this model. What do you need? And query is one, because you need to reflect once to decide out of the 4 positions, but you needed 4 oscillators. This cannot be compressed into 2 bits. There are 4 different physical objects. So now you can see that the quantum case somehow manages to get the best out of both the options. Smallest number of queries and smallest number of space. If you have a particle version, this you can keep the same, but this goes up, penalty, in terms of the query, which represents actually the time of the algorithm. And if you have a wave version, you can save on time, but the space goes up. So this is time. And now you can ask the question of resources. Suppose this is the best of both the worlds, so no problem. You can get the best complexity. But suppose this is not available. Which one out of this you choose? Both are classical, but in different contexts. And that depends on whether you want to save a factor of 2 in time or save a factor of 2 in space. What is more important? And all the complexity analysis, the time and space were basically treated more or less on an equal footing, but that is not true, especially in case of biology. Because in biological system, space is cheap. Time is of essence. Just look at a plant. To continue its generation, need only one seed to succeed. It will produce millions of them. Why? Because that one has to compete with everybody else and do its job fast. Because other competitions from other plants or trees will be there. And if you don't do it fast, you will get wiped out. The space is made cheap. Lots of seeds are produced. Ultimately, only one has to work to go to the next generation. And that is a asymmetric scenario. And then you say that, yes, if time is important, I will go to this strategy, classically. And that comes back to all these kind of models and colliding blocks. I can use that and well, maybe the genetics is using it in this context. Maybe it is classical, but it wants to save time. That is the essential point of biology. And the space can be extra. There are millions of cells in our bodies. Many of them are doing the same job. But yeah, you want some of them to continue with a successful rate, and this is how it manages. So again, there are connections, and as I said, I worked on this stuff for a long time, trying to unravel all kind of hidden factors in the biological case, and the question is open whether it has any relevance to what is our basis of our genetic system. So yeah, this is enough for the day. I will stop here.